Guys, welcome to Physics 114. I'm Bob Polis. I'm the lecturer for this course. Down there is my email. The topic of this course is going to talk about life on the Earth and life elsewhere in the universe. Now, in this course, my office hours are going to, in principle, they could be at any time you want. Office hours are going to be conducted over Zoom, so you could obtain a downloaded copy of Zoom through that website. When you download Zoom for teleconferencing, you will have options, but you do not need to purchase any upgraded plan. For the purpose of office hours, the free version of Zoom will be completely sufficient for what we need to do. So after you do that, if you want to talk over office hours, just send me an email. We could coordinate a mutually convenient time, and then you could ask whatever office hours related material you want to ask. The grades for this module will be distributed roughly as follows. The homework will be 50% of the module grade, and the lowest homework score in this module will be dropped and not counted towards that 50%. The homework, the exam, and the paper should all be sent to me by email. My email is in the syllabus posted on Blackboard, sent out to all you guys today, and also on the first slide in this PowerPoint presentation. I would strongly prefer you submit your homework as an attached Word document or as an attached PDF. I will accept if you send me an attached photograph, but I really prefer you sending me a Word document for your homework. Late homework will accrue a 5% penalty per day late. So if your homework is 1 day late, sometimes things happen. It's not the end of the world, but get it into me. And I'll give you more details on the paper and the exam later on in the module. So if you want more details, see the syllabus, which is posted on Blackboard, for more information about what I expect for these graded items. Now, the textbook for this course is not really going to be that important, so if you did not take the previous modules, you could probably get away without having to purchase the textbook. We will only cover one chapter from the textbook. That chapter is not very long. Everything necessary for this course will be uploaded to Blackboard or YouTube. The book is useful. I will follow along with the book, but like I said, there's not much material on this topic in the book, so there isn't too much for it. If you wish, you could purchase an e-text from the publisher to rent for a few months. There are other options. If you want to go to some online retailer and buy an old or other version of an astronomy textbook, you could absolutely do that, and you should be just fine. The exam at the end of the course is going to be a take-home exam. It's basically going to resemble a really large homework, and you'll have about 1 week for the exam. The exam then, when you're done, you'll email me the exam, and the exam has to be turned in on time. I'm going to be strict about this. The exam will accrue a 20% penalty per day late. And for more details on this, you could look at the syllabus for this course. So let's talk about the concept of extraterrestrial life. Is there life elsewhere in the universe? If the universe is infinitely large, then the answer to that question is absolutely, there definitely is life elsewhere in the universe. Now, this is not any really profound idea that we're discussing here. What we're talking about here is just a generic consequence of the notion of infinity. In the previous module, we said that we know the universe is really large, and the universe very well might be infinitely large. So here's a picture of the large-scale structure of the universe. Now, this image is just a simulation of what the universe looks like on the largest scales, but we do have astronomical surveys that map the position of galaxies and galaxy clusters. We have computer simulations that simulate the growth of galaxies and galaxy clusters. And the surveys, which is data from the real universe we live in, do very well match what simulations predict the universe looks like. The pictures from the simulation are much nicer, so I went with a picture from a simulation. But this, we are confident, is a very accurate representation of what the universe looks like on the largest scales. So here we have clusters of galaxies are gravitationally bound together. They form filaments and sheets of structure. And then between these filaments and sheets, there are voids where there's very little material. Voids are not completely empty, but they're relatively empty. Now, each pixel in this image is a cluster of galaxies. So each pixel that in yellow is many galaxies. Each of those galaxies contain many stars, and most stars contain planets. So the universe on the largest scales is often compared to resembling a cobweb-like structure. Now, since the Big Bang, there has been light from distant objects that has been traveling towards us. So objects give off light, and then that light will spread out in every direction. And there are some objects, the light they emitted is coming towards us, in addition to going in other directions as well. So here's the Earth. I just drew the Earth a little bit bigger than a galaxy cluster just to make it easy to see. And there are objects that are shining light, and that light is moving towards Earth. So here's a really big cluster of galaxies, probably a supercluster, and it's shining light towards Earth. There's going to be a galaxy here shining light in every direction. Some of that light is going to be moving towards Earth. Now, really far away objects, it takes their light a long time to reach the Earth. And really, really far away objects, it takes their light even longer to reach the Earth. Now, there are regions of the universe that we cannot observe because they're so far away that light, which travels at the fastest speed possible, has been traveling since the Big Bang, pretty much. So light has been traveling at the fastest speed for the greatest possible length of time, and that light still has not had enough time to reach the Earth. So there certainly are galaxy clusters out here really, really far away, but they're so far away. Light has been traveling since the Big Bang, and they're just so far away. That light has not had enough time to reach us. And so everything that we cannot see as a result of this is referred to as being beyond our horizon. You can't see over the horizon. Some objects are so far away that light has not had enough time to reach us from them. So we know there is more stuff out there, but we just are not able to see it because the universe is not old enough. We talked about horizons in the previous module. If you want, you could look at the end of the PHY 113 lectures posted on YouTube, and where I talk about horizons more. And in this discussion, I also did not talk about the expansion of the universe, but the expansion of the universe is another problem that will make it even more difficult to see these really far away objects. Now, as a thought experiment, let's assume the universe is infinitely large, and let's pick a region of space. Now, this region of space could be any size you want. So the region of space might be the size of a coffee mug, or it might be the size of a basketball, or it could be the size of the Earth, or anything else. Pick a region of space. Now, within this region of space, there might be some number of particles. There might be 0 particles, or 1 particle, or 10 particles, or 100 million particles. But there is always going to be a finite number of particles inside that region of space. The reason for that is you cannot just cram an infinite number of particles into a region of space. The reason this limit exists is if you put more and more particles into a region of space, eventually you would pack so many particles into a region of space that that region would just collapse into a black hole. So to avoid your region of space becoming a black hole, you cannot put an infinite number of particles into that region of space. So what we're claiming is within a certain sized region of space, there is a maximum number of particles that you could put inside that region of space. This number is going to be less than infinity. So similarly, within a certain sized region of space, there is a number of arrangements of those particles, and the number of possible arrangements of those particles in that region of space that you're considering is also going to be something less than infinity. What do I mean by this? Let's think about a large sports stadium. So This large sports stadium, there are a lot of seats in the stadium. But the thing is, the number of seats in the stadium is not infinity. So there are a finite number of seats in the stadium. We could fill every seat with a person, and you could choose to rearrange how the people's seating arrangement, and then you could rearrange the seating arrangement again. There are going to be a lot of people in the stadium. There are going to be a lot of possible arrangements, seating arrangements of people in the stadium. And when you're talking a stadium that holds tens of thousands of people, there's going to be a huge number of seating arrangements in the stadium. But the number of possible seating arrangements in the stadium is going to be something less than infinity. Admittedly, the number of seating arrangements is huge, but it is less than infinity. Let's assume that within our region of space that we are considering, it could be any size again, coffee mug, basketball, the size of the Earth, anything you want at all. There are a number of particles inside that region of space, somewhere between 0 particles and the maximum limit to prevent that region of space from collapsing into a black hole. And let's also assume that these particles are more or less randomly distributed throughout that region of space. Now, my claim is that if the universe is infinitely large, you would expect that every possible arrangement of particles inside some region of space will be repeated. Because all we're doing is we're saying, here's several regions of space, and there is within this region of space, there's a certain arrangement of particles. Within this region of space, there's a certain arrangement of particles. If the universe is infinitely large, and if particles in the universe are more or less randomly distributed, you expect that at some point, due to the universe being infinitely large, this region of space should be repeated somewhere. Now, the larger a region of space you are considering, the more particles, the more arrangements, you would be less and less likely to eventually find that region of space perfectly copied. But at some point, you're going to find a perfect copy of that region of space again. Because the universe is infinitely large, eventually you will come across that region of space being repeated. So this is one way of thinking about what is a parallel universe. If you think about you are an arrangement of particles. There are atoms that make up your body, and so that is a certain region of space. I fill a region of space that is maybe like 1/10 of a cubic meter, or maybe 1/5 of a cubic meter. There is some number of particles, atoms that make up my body, and I expect somewhere in the universe, the arrangement of atoms that make up my body should be repeated just by random chance. And it's possible to calculate that at about 10 to the 10 to 28 meters away, there should be an identical copy of me. The exact configuration of every particle in my body will be repeated if the universe is infinitely large. Now, what if the region of space is bigger than me? What if the region of space is a sphere of radius 100 light years that is centered on the sun? Well, it's a greater distance away, but eventually this region of space that contains a star like the sun with Earth and Jupiter and Venus and the nearby stars Alpha Centauri, Vega, Sirius, a perfect arrangement of all the particles that makes up our local region of the universe should be repeated. And if we go out even further, let's look at the observable universe, which is known as the Hubble volume. The Milky Way galaxy, Andromeda, the Sombrero galaxy, all of these galaxies are just really big arrangements of particles. And all of these arrangements of particles are going to be repeated in an infinitely large universe. This is just, again, a notion of the concept of infinity. So if you want an interesting read on parallel universes, this is a low-level parallel universe where we just say the universe is infinitely large. And at some point, if you go further away than the observable universe, you begin to see things being repeated. So here's an interesting PDF on this topic. A consequence of this is if the universe is infinitely large, then every possible configurations of particles inside any finite size region of space will be necessarily repeated an infinite number of times. What this means is there are an infinite number of copies of you if the universe is infinitely large. So you are not unique. You are repeated in the universe an infinite number of times in this scenario. So you are not unique. And if we extend this idea even further, any possible creature that does not break the rules of nature will exist in an infinitely large universe. If delicious toaster pastries playing basketball is a possible configuration of particles, if it doesn't break any of the rules by which nature operates, then somewhere in the universe there will be delicious toaster pastries playing basketball. And if the xenomorph with the chestburster and the facehugger aliens, if that creature is somehow physically possible to exist, then that creature will exist somewhere if the universe is infinitely large. As long as that creature does not break the rules of physics, then that creature must exist, because fundamentally that creature is just going to be a certain configuration or arrangement of atoms. And somewhere, if that creature is allowed to exist, there is somewhere where this creature exists on the same planet as people. Now, this discussion that we had did assume that the universe is infinitely large. Currently, to the extent that we could tell, our best data does not discriminate whether or not the universe is infinitely large versus just really large but with a finite size. If the universe is closed and has a finite size, then this discussion doesn't apply. And again, to see about a finite-sized universe that's closed versus a flat or open universe, which are infinitely large, I'll refer you to some of the previous lectures from 113 on YouTube. So the universe might be infinitely large, or it might not. Right now, the error bars for what we are confident in do allow for both possibilities. So some of the ideas here that I talked about today overlap with ideas from Physics 113. And like I said, all the lectures from 113 are available to watch on YouTube. So in the next video, what you're going to do is you're going to watch the Kurzgesagt video on emergence.